Start now. Okay, so today we are doing the set 5 revision. And if you look through the questions, right, the first few questions are all older questions. And we are not going to be doing that today. We'll be doing the newer questions, which I've cut out towards the end. So questions 4, 5, and 6, okay, these are the 2022 questions that from the recent prelims. We're going to be focusing on that during lesson. Next lesson also same thing. We are just going to be focusing on the newer questions. Okay, so we are just going to start off. Go to question 5. Yeah, this Hua Chong prelim question. And I just want you guys to do part A and part B first. Okay, just 5A and 5B. I will give you guys 10 minutes, right? 5A and B only, 10 minutes. Okay, so I'll time you guys, same thing. Right, okay, let's just begin now. Okay, time's up, right? Let's go over this first part of the question. Right, okay, so let's look at part A first. Part A, so far, nothing too crazy going on. Okay, part B starts to get a bit crazy lah. Right, okay, but part A, right, definition, and in part 2, okay, part 2 usually, right, when they ask you to explain color, that part is usually 3 marks. Okay, you can expect to see 3 marks in A levels, but this one's a bit more demanding because they want you guys to explain why it changes color when you add ammonia. Okay, a few things. I want to discuss this second half of this question. Okay, because I need to see some keywords in your answers. Okay, because it's not easy to get this last mark. Okay, first of all, the fact that they mentioned aqueous, and then it already implies that there are water ligands, right? And then afterwards, okay, when they change color, it's because they have a different ligand. Okay, so I need to see the word ligand exchange in your answer. Okay, even though it's only 1 mark, okay, it's quite demanding in order to get this 1 mark. Okay, so let's take a look at the answer here. Okay, again, I'm not going to go over part 1 because it's just a definition question. And I'm not even going to go over this part because this is just a very standard transition elements question at this point. Okay, you just have to get the full marks when you see this question from now on. Okay, but it's just this part over here that I just want to focus on. Okay, you're required to use the word ligand exchange, okay, because you need to acknowledge the fact that you have a different ligand, and it is because of a different ligand you get a different color. Okay, but how do different ligands get different colors? You need to link it up using the words, okay, splitting d orbitals to different extents. And because of that, you have different energy gaps. Okay, I need you guys to also highlight the word energy gaps in your answer. Okay, so these 3 words, okay, then can get yourself your final 1 mark. Okay, so quite a demanding question, okay, because usually for 3 marks, the first half would suffice, okay, but not the case of this question here. Okay, so that's that for part A. And then let's move on to part B, right? Part B, let's break it down first. Okay, this is a typical ligand exchange reaction involving a bidentate ligand. Okay, you have seen this bidentate ligand many times, and they just ask a few questions now. Okay, entropy, they love asking about entropy, right? Okay, entropy of this reaction here, they said is large and positive. Okay, so your answer, right, actually has to be split very clearly into 2 parts. Okay, you have to first explain large and then explain positive. Okay, in whatever order. You have to make sure your answer is very clearly okay, explaining positive, and then the second half of your answer is very clearly explaining large. Try not to conflate both together because it's quite common. Okay, you guys tend to conflate both ideas together without actually realizing. And if your examiner can't differentiate the 2 parts of your answer, then it is hard for them to give you the marks as well. So you want to make sure next time, right, if they ask you to explain 2 aspects, your answer is split clearly into 2 aspects. Okay, so I'll show you guys what I mean by that. Okay, but first, it's always easier to explain why it's positive. Okay, the sign. Okay, this kind of questions, they're asking for both the sign and the magnitude. Usually you want to try to explain the sign first. It is easier. Okay, because over here, okay, we have 4 aqueous species, then it increases to 7 aqueous species. So there's more number of ways to distribute the particles and its energy. And as you can see, okay, that explains positive increase in entropy. Okay, but it's very easy, right, to also talk about the magnitude at the same time because 4 to 7 seems like a huge jump, right? Okay, which it is. Okay, but you should explain that separately. Okay, to explain why it is large, okay, you must tell me that 7 is a lot greater than 4. You have a lot more aqueous species. Sorry, you have a lot more aqueous products compared to the amount of aqueous reactants. So having much more products than reactants will result in a large magnitude. Okay, so try not to conflate both together. Okay, you should be separating your answer. So that's why you see in my first part of my answer, right, I only address the idea of positive. I address the sign first, and then later on, right, I address the magnitude on why it is very large. Okay, there are some keywords to help. Okay, there are some keywords to help you separate your answer so your examiner knows where to give you your marks. Okay, the first word I use is magnitude, and then they will know that this second half of my answer is to address the magnitude. Okay, the first half, okay, you can just say the increase in number of ways to distribute the particles. Okay, that's to address positive. See, when you split your answer like this, right, okay, then it's clear enough. Okay, a lot of your answers, when I see this question, a lot of your answers tend to be very similar, like the large and the positive, I can't differentiate, then I can only give you guys 1 mark. Okay, that's what the examiner's perspective will look like, right? Okay, then the next part over here is just delta G. delta G is, okay, I've got a question in the chat. Delta G answers over there. Okay, you guys can just mark your answer. In the meantime, I'll answer the question. Same thing, whatever questions that you guys have, please type it in the all chat, because if you direct message me, some of you guys just have no idea what's going on as I'm explaining. But anyways, the question someone asked is, shouldn't we distribute energy and not distribute particles? Okay, guys, distribute particles, distribute energy, both are included in the definition of entropy. Okay, so if you say distribute particles or you say distribute energy, right, it's honestly the same thing. Doesn't matter all that much. You want to say distribute particles and energy, even better. Okay, but that's not a very significant part of the explanation now. Right, okay, so that's for part 2. Part 2 should be very simple. Okay, then we look at part 3. Okay, so for part 3, they ask us to talk about how delta G relates to position of equilibrium. Okay, so let's discuss that first. Okay, now first of all, right, a negative delta G, some of you guys just tell me is spontaneous, but that's not specific enough. To improve your answer, right, okay, what I suggest you guys tell me is this. A negative delta G implies that the forward reaction is the one that is spontaneous. Because this reaction that we are talking about, right, is a reversible reaction, it is unclear if you just tell me the reaction is spontaneous. What reaction? Is it a forward reaction or backward reaction? Okay, so you just have to specify whatever you calculate is always about the forward reaction. Okay, and that's why the position of equilibrium lies towards the right-hand side. Okay, so that's the first part of our answer over here. Delta G negative means forward reaction is spontaneous, POE lies to the right. Okay, what does that tell you about the ligands? Okay, if you see which ligand bonds preferentially. Now, first of all, okay, you must recognize the reaction is a ligand exchange reaction. And we've talked about this before. Strong ligands replace weak ligands, right? So in other words, over here, if the POE is favoring the right-hand side, it implies that this ligand wants to exchange this ligand. And that implies that the bidentate ligand is stronger than the monodentate ligand. We've done a similar question the other time, okay, where they asked us to use delta G to infer which ligand is stronger. Not many lessons ago, we did this. Okay, but on the other hand, you can think about it this way. If the POE lied to the left instead, then what does this mean? Okay, it means that your ammonia wants to replace the bidentate ligand, right? And that implies that the ammonia is a stronger ligand than the bidentate ligand. Okay, but clearly that's not the case here. You don't have to explain all this in words. Okay, all you need to do over here is just infer, because they tell you hence identify. So you just need to identify over here. The bidentate ligand is a stronger ligand. That's why it binds preferentially. Okay, that's the word that I will use over here. Okay, so I recommend including the word stronger ligand, okay, because that's what we can infer from this reaction. Okay, so far. All right. Okay, and now I will talk about the last part, part 4. Part 4 is a bit weird, okay, because it's one of those questions where it's not worth your time to get that 1 mark. It's really not worth your time in exam. Okay, but if you really want to give it a go, okay, then it's up to you. Okay, but let me just flash the answer key to you guys for part 4. Okay, they are saying, right, why is a bidentate ligand faster than a monodentate ligand? You have never learned something like this before. Okay, that's why it's a suggest question. Okay, but let's look at the first answer, right? Okay, I will talk about it. Okay, you can read the first answer and I will just attempt to break it down, okay, to make it a little bit more layman, right? Just take a look at this first answer here. Okay, so you might want to focus on these 2 keywords, okay? And let's just see what they are trying to explain. Okay, they are saying that a bidentate ligand, which looks like this. Okay, let me just draw it out first, versus a monodentate ligand, right? The bidentate ligand, right, okay, to bind the first amine, it is intermolecular because it's across 2 different molecules, right? Okay, but then the moment the first one is binded, right, the second one is much easier to bind because it is now an intramolecular reaction. It is now happening within the same molecule. It's not across 2 different molecules. Can see that? Okay, if let's just say, let me just draw it over here. Okay, let's just say this is the central metal ligand. Okay, it can be cobalt or whatever. Okay, when they bind the first ligand, it is an intermolecular reaction. It's across 2 separate molecules. Can see that? Okay, across 2 separate molecules. But then to bind the second molecule, as you can see, right, it is already considered 1 molecule. So it's intramolecular, and this happens to be faster. Okay, so that's what they're trying to say over here. Okay, the phrasing and all that you guys can learn from it. Okay, but that's what they're saying in this question. Okay, but let's take a look at the second reasoning. Again, this second reasoning, right? I really don't expect you guys to be able to word for word come out with this in an exam. It's really not worth it for 1 mark. Okay, but what they're trying to say here is, okay, coming to this equation here, if you want to bind the bidentate ligand, you only need 3 molecules. But if you want to bind a monodentate ligand, it requires 6 of the molecules. Colliding 3 molecules has a much higher chance than colliding 6 molecules. Can see that? Okay, it's the idea of collision theory and effective collisions. Colliding less molecules together is more successful. There's a higher probability of success as compared to having to bind so many different molecules together. The chances of success is much lower. Okay, so that's what they're trying to say in this second answer, which I personally prefer, but it's just harder to write it out in exam. Okay, it doesn't have to be word for word. If you have something similar to this, I would honestly accept the answer also. Okay, so part 4, quite tricky. Okay, and if you guys have no questions over here, okay, I will want you guys to complete part C. Okay, part C shouldn't take very long also. I'm gonna give you guys only 5 minutes to complete the rest of the question. Okay, so if you have no questions, okay, just start with your part C. Right. Okay, time's up. Right, let's go over answer. Okay, so this next few parts quite short. Okay, but just need to understand a few things. Okay, when it comes to chirality, right? Okay, you guys only know chiral centers existing in organic chem, right? Okay, so it's a little bit weird to see chiral compounds existing outside of organic chem. Like right here, this is a complex. Okay, we've never learned how complexes can exhibit chirality. Okay, but so you just need to draw the structures as per normal. Okay, so of course there's only a couple of ways to draw this out. Okay, they said that you have to draw two enantiomers. Okay, meaning to say, right, this has to be the normal image, and then the next one, whatever you draw, right, you have to flip it. Okay, so that means the other species has to be the mirror image of the initial compound. Okay, so for the first structure, right, you can draw whatever configuration you want, but the second structure you can't. Okay, but take note, there's only a limited number of configurations you can have. Like you can have, you can't have something like this, for example. Okay, because it is not possible to fit the final ligand into your answer. Okay, it's not possible for a bidentate ligand to appear at the top and at the bottom. Okay, it just doesn't work. It's too far. Okay, so okay, if you want to position it like this, okay, okay, then afterwards you need to position the other two, so you have one more over here and then one final one over here. Okay, and that's how you can position the three different bidentate ligands around this compound. Okay, so that's basically how it's done. Okay, just fill in all the H's. You can make sure that your H's are not bonded to the central ion. The central ion is the one that is bonded to the nitrogen. Okay, so once you have drawn whatever configuration that you have, right? Okay, the next thing that you need to do is to flip it. Okay, and how do we flip it? Okay, let's just start with here. When you flip this, you'll end up over here, right? Okay, so you just have to position it correctly. And then from there, you just flip the rest also. These two you flip already, they'll end up over here. Okay, so you draw them. And then finally, this one, you flip already, you end up on these two spots. Okay, so you end up one here, you end up one here, and you end up with something like this, though. Okay, fill in all the H's, and then that's pretty much your answer. Okay, so basically this question here, right, the only thing that you're looking out for is to flip the other structure around. So this has to be the mirror of the first structure. Okay, as to how they are considered chiral, okay, you just have to fall back onto your very fundamental idea of chirality. What is the criteria in order to exhibit enantiomerism? Okay, so remember that there are two criteria to fulfill. The first criteria is non-superimposable mirror images. And that's basically what you need to write over here. Okay, I know it's very difficult to visualize that here because number one, we have never learned chirality for complex ions. And it doesn't matter. Okay, because, let me just explain briefly why is chiral. It doesn't look chiral at all, right? Okay, based on your own knowledge of chirality. Okay, but because they are all existing across different planes, you can see this different plane already. This one also different plane. And because they're all existing in different planes, right? Okay, it does allow for some sort of chirality. Okay, so the first answer over here, right, is you must tell me, okay, the mirror image, right, is actually non-superimposable on the normal image. Or you can say non-superimposable on itself. That is the fundamental idea behind enantiomerism. So why is it considered chiral? You just have to fall back onto this. Okay, and the reason why it's non-superimposable is again because they all exist in different planes. Okay, you can see the three different bidentate ligands exist across all the different planes. Okay, the second one that you can also discuss, okay, is no internal plane of symmetry. Now you don't need both. Okay, as long as you have 1 point, right, you can get a mark already. Okay, again, it does look symmetrical, but again, because they're all existing across different planes, okay, it's actually not symmetrical internally. Okay, so it can rotate plane polarized light and all that. Okay, so you just have to have one of these answers. Okay, so from now on, right, okay, you should just treat this as, you shouldn't overcomplicate it, okay, don't need to overthink it. Okay, complex ions, some of them are chiral. Okay, and the reason behind it is just whatever that we learn in our syllabus. They will never test you anything that's beyond the syllabus when it comes to enantiomerism. Okay, and then the last one should be quite simple because we've gone through this before. Okay, physical properties. Okay, we have gone through enantiomers, right? Okay, physical properties are all the same. Okay, so enantiomers have the same boiling point, the same melting point, same density, same solubility, everything. Okay, it's exactly the same because they are, after all, just mirror images of one another. Okay, but the one difference is that one exception. Okay, the only exception here is the direction of rotation of plane polarized light. You need the whole thing, direction of rotation of plane polarized light. And that's pretty much your answer to this question already. Okay, so you can just pick and choose, pick one. Okay, I say that same boiling point. Okay, then I can say different rotation of plane polarized light. All right, okay, and that's your answer for this segment here. Okay, quite likely that they will ask you to draw enantiomers in exam, so just be prepared for that. All right, okay, and with that said, okay, that concludes this question. Again, if you have any questions, okay, just type in the chat. Okay, but we shall look at the next question now. Okay, we will proceed over to question 6. Okay, question 6 is quite a long question, so I will want to split this into 3 parts. Okay, and I want you guys to do this first part first. Okay, and I'm gonna give you guys only 7 minutes, okay, to do 6 part A. Okay, 7 minutes for this part because no application involved. This one is all just content knowledge. Okay, so this one shouldn't be too difficult. Okay, and we can just start now. All right, 7 minutes. Right, okay, time's up. Right, okay, let's just get this two parts out of the way very quickly. Right, first part is just a very standard mechanism question. Okay, second one is just synthesis. Okay, I'll go through the synthesis in a bit. Okay, but let's take a look at the mechanism first. Okay, mechanism wise, just go and check. Okay, this is about aqueous bromine. So just make sure that the second step, right, the nucleophile is actually water. Okay, but when it comes to drawing water, right, you just have to take note of this part over here. Okay, you need to show how water's extra hydrogen is being deprotonated. Okay, as you can see over here now. Right, okay, the arrow movements and all that, okay, I don't have to explain. Okay, I think should be, I've explained enough for when it comes to the arrow movements. Okay, positive charge and whatnot. Okay, take note, right, you are expected to draw the major product when you do any mechanism. Okay, so the major product here must follow the Markovnikov's rule. Okay, so that's that for that first part. Okay, and then let's take a look at part two. Okay, if you want to break down part two, again, it's all just, let's follow the steps that I've taught you guys when it comes to reaction mechanisms, reaction synthesis. Okay, so anytime you see a synthesis pathway, the first thing you always need to do is to count the number of carbon atoms. So we have 4 carbon atoms, and then at the end of the day, we have less. Okay, so there is a step-down reaction, and the first step-down reaction that comes to mind is usually your iodoform test, right? And as you can see here, this guy is clearly eligible for the iodoform test. So why not let's do that in the first step, right? Okay, so the first step here, I can get an iodoform test, and I will get myself my carboxylate salt. Okay, but if you realize something, okay, we don't really deal with carboxylate salts, especially when we want to continue the reaction, right? We want to turn it into other things, okay, from structure D to compound E and so on and so forth. Okay, so maybe the carboxylate salt is not the best way because we can't really proceed from there. Okay, so instead, perhaps what you should do is you should turn it back into a carboxylic acid, because once you have done that, then it's a lot easier for us to proceed to step 2, right? Okay, because carboxylate acids can undergo a lot of different things. So we need to eventually turn it into an alkene. Okay, what can we do to a carboxylate acid? How do we get rid of the carboxylate acid? Okay, we can undergo reduction, right? We can reduce it back into a primary alcohol like this. Okay, that's the best way to get rid of the carboxylic acid. And then afterwards, okay, the final step here is just to dehydrate the alcohol, and then you can get yourself your alkene. Okay, so as for the synthesis wise, okay, that's pretty much the answer. Okay, you see, right, once you've identified step-down reaction, a lot of the things start to flow. Okay, but if you don't identify step-down reactions or even step-up reactions, okay, it gets very difficult. Okay, so later on in the lesson, we will try another synthesis, which is a little bit more challenging. Okay, so that's just pay attention to that. Okay, take note, this is iodoform test. Iodoform test is done in alkaline conditions. That's how I get carboxylate salts. Okay, but I want to protonate it, right, to become carboxylate acid so that I can undergo further reactions. Okay, so I actually added this in over here, followed by H2SO4. Okay, I want to protonate the salt to turn it into a carboxylic acid. Okay, as for the rest, okay, this should be quite standard. Okay, dehydrating agents, you have 2 options over here, 2 of the more common options. Right, okay, if not, right, okay, we're just gonna not waste any more time and then just proceed to the next part of the question. Okay, so I want you guys to turn over to part B. Okay, again, just do B part 1 and B part 2. B part 2 is 5 marks. Okay, so I'll give you guys a bit more time to write your answer, substantiate your answer. Okay, let's make sure your answer can hit all 5 points. Okay, so I'll give you guys about 8 minutes, right? Okay, for this part B. Right, okay, so again, question 6B. Okay, I'll give you guys 8 minutes. Okay, most of your time should be spent on part 2. Okay, don't spend most of your time on part 1. Right, okay, so let's just begin now. Right, and time's up. Okay, that was 8 minutes. Okay, let's go over this question. Okay, for this question, it's especially part 2, there's a lot of things to write. Okay, and because there's so many things to fulfill, let's break that down first. And then later, right, and then I will show you guys what we are expected to do, okay, to answer these kind of questions next time. Okay, so this question here, okay, I'll go through the dot and cross later. We talk about part 2 first. There are 2 parts to this question. Okay, the first part is to explain the acidity, as you can see. Okay, that's the first part. The second part is to explain why only one of them produces the white precipitate, which is your AgCl, and why the other 2 don't. Okay, and clearly they ask us to explain in terms of the reactivity. So there are 2 concepts here, called acidity concept and reactivity concept. Okay, let's explain the acidity concept first. Okay, we are meant to assign all these pH values to the correct species, and let's start with the strongest acid. Okay, the lowest pH. Now the lowest pH is 0.5. Okay, and some of you guys will say that it belongs to the acyl chloride. Okay, that's correct. Okay, but I want you guys to first understand, right? Acyl chloride is not an acidic functional group. Okay, don't be mistaken. Okay, it is not an acidic functional group itself. Okay, but it creates an acidic solution because acyl chlorides can hydrolyze in water, which then creates the acidic solution. So without water, right, acyl chlorides are quite useless on itself. Like it is not acidic. Okay, because a couple of reasons, it just doesn't have a hydrogen to dissociate into. Okay, like you look at the functional group here, there's no hydrogen, you can't dissociate to produce H+ ions. That is what makes something acidic. Right, okay, carboxylic acid is acidic because you can dissociate to produce H+. So as for acidic functional groups, in your syllabus, you only know alcohols, phenols, and carboxylic acids. Acyl chlorides are kind of different. Okay, so how does it actually work? Acyl chlorides, when reacted with water, this is your hydrolysis reaction, and you form back your carboxylic acid. But mainly the reason why it is the pH is so low is because you form your HCl molecule. HCl is an acid, a very strong acid. Okay, and because of that, right, he's the reason why the pH is very, very low. That's why he has the pH of 0.5. You need to bring out that idea over here in the answer. Okay, so don't tell me anything about stability of conjugate base, right, when it comes to acyl chlorides, because there's nothing to explain that. Okay, he's not even acidic. Okay, it's because of this guy, actually. That's why he's acidic. Okay, then of course, okay, we are next asked to assign between 2.5 and 3. So 2.5 is stronger acid than 3. So we have to compare between the 2 carboxylic acids. Okay, as you can see over here, the difference between the 2 is that this guy here has a Cl group. Now this Cl over here is your electron withdrawing group, right? Okay, so you just have to mention that electron withdrawing group disperse the negative charge on the conjugate base. That's why it stabilizes it, making it a stronger acid. Okay, very classic answer over here. So whatever that we have so far, right, okay, is total of 3 marks to explain the acidity. Okay, so I'll show you guys the answer later. But now the next thing that we also want to explain is this white color precipitate. Why is it that only one solution gives you the white precipitate when you add aqueous silver nitrate? Okay, so first of all, that one guy has to be your acyl chloride, because acyl chloride is the most reactive functional group. Here we have to discuss reactivity, and the thing is, what are we supposed to compare it to? Okay, we can't just explain acyl chlorides alone, we have to compare it with something else. Okay, and take note, you're not supposed to compare this with a carboxylic acid. You're supposed to compare it with specifically this compound over here. Now, why this compound? Because remember, when it comes to chlorine-containing compounds, there are 3 types to explain. The first is acyl chloride, second is alkyl chloride, the last one is your chlorobenzene, which is not in this question. Okay, so you have to compare it with this compound here. Okay, so it's between compound J and compound H. Okay, so how to explain reactivity? Okay, this guy bonded to 2 highly electronegative atoms, so that's why the carbon is super electron deficient, very susceptible to getting attacked by a nucleophile. This guy only bonded to chlorine, so the carbon is not as electron deficient. He will not be attacked as readily by a nucleophile. So in other words, okay, this guy is super readily attacked by a nucleophile. Okay, what is the nucleophile here? It has to be water, right? Because you're adding aqueous silver nitrate. So aqueous silver nitrate, the water first comes in, the water will hydrolyze this guy first. Okay, it will hydrolyze the acyl chloride first, and this Cl atom will be liberated, right? And then once it's liberated, then that's how the AgCl white precipitate is formed. Okay, which you need to acknowledge your answer also. Okay, if you never talk about AgCl in your answer, okay, then you can't get the final mark. Okay, so there's two parts to this question. Okay, difficulty-wise, it's not difficult, but it's just that you need to explain a lot. Okay, so let's take a look. Okay, now, look at the mark allocation. Okay, the first part of the answer is to talk about your acidity. Okay, you first explain the acyl chloride hydrolyzed in water to produce strong acid HCl. Okay, you need that part for 1 mark, and then I assign a value. Okay, electron withdrawing, blah blah blah. Okay, then that's another mark. And then finally, when you assign all the pH values, that is the final mark. Okay, so there's 3 marks for the acidity portion. Okay, as for the 2 marks for reactivity, okay, quite demanding here, but I just want you guys to take note of 3 keywords. Okay, first you talk about the 2 highly electronegative atoms. That's why the carbon is very electron deficient. That's why it is more susceptible to nucleophilic attack. Remember, you need these 3 parts, right? Whenever you explain acidity, whenever you explain reactivity questions, you must have these 3 parts in your answer. Okay, that's for 1 mark. And of course, then you link it back to the white precipitate. Okay, the Cl atom is liberated as Cl minus, which then reacts to form the AgCl. Okay, that's your final 5th mark. All right, okay, so that's what we have for this portion here. Okay, and then we have the answer for part 1 also. Okay, if I don't think I will need to explain how to draw a SOCl2. Okay, Cl can only form 1 bond because Cl, it has 7 valence electrons, so you can only form 1 bond. Oxygen has to form 2 bonds. Okay, but first of all, before all this even started, you need to first determine that sulfur has to be the central atom. Okay, why sulfur? Why not oxygen? Okay, why not chlorine? Okay, because sulfur can form the most number of bonds, right? Okay, it can expand its octet and it can form the most number of bonds compared to the rest of the atoms in this molecule. Okay, that's why it has to be at the center. Okay, trigonal pyramidal 107 degrees. Okay, that's that. All right, Ken? Okay, any further questions over here? Okay, that's for part B. Not a difficult question. Okay, just make sure you have all the grounds covered. Okay, but we're going to move on to the important part of this question, which is that final part. Okay, this question here, this final part of this question is the reason why I even picked out this question in the first place. Okay, so I want you guys to turn over to this acid-based looking portion. Okay, and I will give you guys a bit more time because I want you guys to make sure you try every part. Okay, it's 12 minutes. Okay, I'll give you guys 12 minutes to do this last part here. I think this is a very well set question. Okay, it's not very easy also. Okay, so I'll give you guys a bit more time to think about this. Okay, take your time to do the parts in this question because I think it is worth it. Okay, so 12 minutes. Okay, we shall start now. All right. And time is up. Okay, so let's go over this question. Okay, there's a lot to discuss in this question. Okay, a lot. Okay, and we will break it down first. Okay, and then all the other issues will surface later on. Okay, so this is a rather unique experiment because we are seemingly just doing a titration experiment, but it's not just any titration experiment, right? Because this one actually precipitates AgCl when you titrate it with Cl minus. So yeah, sure. Okay. And then the next thing is they come out with this very weird little titration curve. It looks oddly similar to a normal acid-base titration curve. And we shall understand why later, especially I think it's part 4, where they ask us to explain why the shape looks like this. Okay, it's like a titration curve. Why does it start so normal and then later it suddenly dips? Okay, it becomes a sharp point towards the equivalence. Yeah, okay, we'll explain all of that later. Okay, but it is good to break down the curve first, right? Okay, to kind of understand what you're getting into. So before I look at any question, okay, let's just understand why this graph looks like this. Why does it start at the top and why does it not start at the bottom, for example? Okay, to gain a little bit of understanding on this question first. Okay, so we know PAG, right, is negative log Ag plus. Okay, and we know that Ag plus is what we are concerned with. So when PAG is very high, that means the concentration of Ag plus here is very low. Okay, so again, let's have a mental picture of what is happening here. We have a solution just filled with Cl minus ions, right? This is a water sample with only chloride ions, and we are trying to see how much chloride ions there are by titrating it with your Ag plus. Okay, so as I'm adding Ag plus inside, right, why is it that Ag plus concentration still stays very, very small, right? Why does it not increase? Because obviously, when you add Ag plus, it doesn't just swim around in the solution, right? It actually comes out as AgCl precipitate. So in the very beginning at the very beginning stages of this experiment, when you add Ag plus, you are not actually causing Ag plus to increase, because the moment you add Ag plus, it is just going to precipitate out pretty much instantaneously. Okay, so Ag plus concentration in the mixture, right, doesn't actually increase all that much, right, at the very beginning, because the moment you add inside, precipitate. The moment you add inside, precipitate. So it doesn't actually contribute to the concentration. Okay, that's why the concentration of Ag plus is very low at the start. Okay, then suddenly, okay, we have the equivalence point. Okay, there's quite a few things to discuss here. Okay, first, of course, you need to recognize that this is the equivalence point. It is the point at which ideally you have most, if not all, of the Cl minus ions precipitated out of the solution. Okay, so I say again, this equivalence point, what does it represent? It represents the point at which you pretty much don't have any more Cl minus, because everything has been precipitated out of the solution already. Okay, so again, right, the idea of equivalence point has always come off to us as a complete reaction, right? Okay, you must have a complete reaction in order to have, okay, the equivalence point as the, okay, in order to see the equivalence point, right? Okay, it has to be a complete reaction. And we also focus on the idea of one-to-one ratio every time we are at the equivalence point, right? Okay, it's the same idea here between Ag plus and Cl minus. It is a one-to-one ratio. Okay, so we will understand this complete reaction more later on as we look into some of the parts. But the idea is that here, you don't have any more Cl minus ions. Then let's look at the next part. After this equivalence point, why does the Ag plus concentration suddenly shoot up so much, right? Okay, because here, at low concentration of PAG, the concentration of Ag plus is very high. Why is it very high? Okay, because at this point, right, you have finished reacting all the Cl minus. So when you add excess Ag plus, can you see it's literally called excess, right? Okay, when the Ag plus is added inside, it is not going to precipitate out as Cl minus anymore. It is just going to swim around in the solution. So now when you add Ag plus inside, it doesn't escape as a precipitate. It just continues swimming around as an ion. So that's the reason why, right, the more you add later on, right, Ag plus continues increasing. It is a very high concentration of Ag plus. Okay, so now that we understand that, okay, let's take a look at part 1. Part 1, they ask us to calculate Cl minus ions using point E. They said we assume all has reacted. Okay, assuming all. Okay, but we know later on in part 3, right? Okay, it is not actually true. Not all of the ions actually precipitated out. Okay, because they said that at this point, point E, there's still a bit of Cl minus remaining. But but we can consider it as most of it reacted over here in order to calculate Cl minus. Okay, so they hinted to us at point E, we can find the number of moles of Ag plus, right? And with that, we can actually find Cl minus because again, it's a 1-to-1 ratio at point E. Okay, then from there, we can find the concentration of Cl minus. Okay, so let's take a look at the answer here. Okay, Ag plus, okay, equivalence point 1-to-1 ratio is the same, and then you divide by the volume. The volume of the water sample is only 25 cm cubed, then you can get that as your answer. Okay, so that's the first part of the question done. Okay, and then let's look at the second part. Now, the second part is yet again a show question. Show that a precipitate will be observed. What does it mean when you want a precipitate to be observed? How do we show that? Okay, you want to show that the IP has to exceed the KSP value, right? That's what it means by a precipitate being observed. Okay, so we have to somehow prove that the IP is more than KSP. Remember, you can't start off your answer with this statement immediately because you're supposed to prove this at the end. Okay, so let's try to prove this statement. So first of all, they say they added this a volume of AgNO3 during the sample. So what we meant to calculate here? Okay, so they said IP is more than KSP, right? So we have to calculate IP. How do we calculate IP? Okay, we know IP in this case is Ag plus times Cl minus. Agree? So we basically have to find the concentration of Ag plus and Cl minus in the mixture now. But take note, okay, currently our mixture is 25 cm cubed, but I'm adding 0.1 cm cube of Ag plus. So can I just say the concentration of Ag plus is just this value over here, the initial value? No, right? Okay, because right now you are pouring this Ag plus into a larger mixture. The volume has changed. And since the volume has changed, that means we need to find the new concentration of these ions. How do we find the concentration? Okay, so remember, there's this formula. You need to find the final concentration. You must take the initial concentration and multiply by the dilution factor, right? Okay, I talked about the dilution factor before. You take the volume over the total volume. This is the factor at which it dilutes. Okay, so let's do this for Ag plus first. Okay, as you can see, Ag plus, the initial concentration is this, but you're adding this volume only. The total volume is 25.1. So this is the dilution factor. As you can see, the concentration is much smaller now. Okay, then you do the same thing for Cl minus. Cl minus is not this concentration because now the volume has changed. So the volume is 25, total volume now is 25.1. So now the concentration is a little bit different. Then once you have gotten all this, okay, you can multiply Ag plus and Cl minus together to find your IP. And that's when you realize it's larger than KSP. Then you can show that the precipitate is formed. Okay, so that's the proving part of this question. Okay, Ken? Okay, so that's for our answer in part 2. Okay, so far, okay, if there's any questions, just feel free to ask. Okay, then we'll proceed to part 3. Okay, so in the first part, we assume that all the Cl minus ions have reacted. Okay, but we have done solubility, you have done KSP, you have done selective precipitation before, right, guys? Okay, since you have done all of that, okay, I'm sure you guys realize, right, that there is no such thing as all the ions disappear. Okay, even though at equivalence point, by right, everything should disappear, it is not the case for most scenarios, especially in real life. Okay, so that's why at point E, right, there are still Cl minus remaining, but it is so small to the point where it's considered insignificant. Okay, and we need to calculate this Cl minus. Okay, so they told us PAG at point E, so we can find the concentration of Ag plus, right? Then how do we find Cl minus? All we need to do is just to sub it into the KSP expression. Okay, so that's what we have to do over here. Okay, convert your Ag plus into concentration, sub it into your KSP, then you can find Cl minus. There's a very small concentration of Cl minus left. You see at the start, we have this concentration, but now we are only left with this. So it can be said that there is a very, very effective separation that is done in this experiment. Okay, so there's a small concentration left in the solution here. That's the answer for part 3. Okay, Ken? And once that is said and done, okay, then we can finally look at part 4. Part 4 is the explanation part of this question, where we are asked to explain why is the gradient at the start very gentle, but it becomes very steep as we pass through point E. So we have kind of explained the gentle part at the very beginning, right? As I mentioned, it starts off at very low concentration and it doesn't change much because when you add Ag plus at the start, it is instantly precipitated out, right? It's instantly precipitated out as AgCl. So the Ag plus, whatever you throw inside, right, will never increase. It won't increase at the beginning, okay? Because the moment you throw in, it come out. You come in, you come out, right? Okay, so it doesn't increase much. That's why the gradient is very gentle. Okay, but then how about this part? Okay, we haven't really explained this. Why does it become super sharp? Why is there a very sharp dip, okay, as we go through point E? Okay, if you notice at point E, this is the point where there's a complete reaction. Let's just once again assume, right, that there's no more Cl minus. And again, at this point, if there's no more Cl minus, whatever additional Ag plus you're adding inside will not precipitate, right? Instead, what will happen is that any additional Ag plus will actually cause the concentration of Ag plus to increase in the mixture. And that's why, right, there's a huge dip. There's a very sharp dip. Because this is the first time, right, okay, this point at which it starts, the first time at which Ag plus actually begins increasing in the mixture. Why does it begin increasing? It's because there's no more Cl minus to get rid of Ag plus. Okay, so that's pretty much the answer to this question here. Okay, so I split it into two parts. Okay, this first part is to explain gentle. When it's first added, it's immediately precipitated out. Okay, again, that is the keyword to this question here. Okay, so that's why it doesn't change much. Gradient is very gentle, decrease only slightly. Okay, but as you pass through point E, right, okay, as I mentioned, we assume all, okay, we assume all the Cl minus has been precipitated out. So any further addition will be in excess. Okay, I use words like this. Okay, you don't have to use all these words. Okay, but it is recommended words, right, to get your point across. Further addition, excess, right, okay, will cause the concentration to increase sharply. Another keyword, increase sharply. Okay, to really make your answer more substantiated, this is how you would do it. Use words like this. Okay, so that's the answer for part 4. Okay, quite an important segment here. Right, any questions so far? Right, should be okay, Okay, then we can take a look at part 5. Okay, so for part 5, it's one of those questions like you will see in your recent practical, right? They always like to make a modification to the experiment, and then they expect you to say how that affects the results. Okay, is your result larger than expected, smaller than expected, so on and so forth. Okay, so let's go over that last part here. So to go through this part 5, what happens when there's a contaminant of ammonia? Okay, so take note, the keyword here is contaminant. What does that mean? Okay, so I'm going to paint two scenarios for you guys. The first scenario is the normal scenario. Okay, so just treat it as if it's normal. You only have Cl minus, there's no contaminants here. And from this question, you need 21.6 cm cube of Ag plus to get rid of all the Cl minus that is in your clean mixture. Okay, but now the second scenario I'm going to paint to you guys is with the contaminant. Okay, so there's Cl minus, and remember, the word here is contaminated, meaning to say the Cl minus, is it the same or is it now different? Okay, it has to be the same. Okay, it's the same amount of Cl minus that's in the solution. Because it didn't affect the Cl minus. They only said there's just an additional contaminant, NH3. It's additional. Okay, it doesn't affect Cl minus. Okay, so yet again, right, to react with all the same Cl minus, do you agree, right, that you still need 21.6 cm cube of Ag plus? Minimally, you still need this amount to get rid of your Cl minus because the Cl minus is the same, right? But how does your ammonia come into the picture? Take note, right, that your ammonia can react with Ag plus, right? Okay, ammonia and Ag plus can react with each other to form the complex. So now that you have additional NH3, do you see, right, that this requires a little bit more Ag plus than expected? Okay, let's just say you need 3 cm cube of Ag plus to get rid of the small amount of contaminant. Let's just say, okay, you only need 3 cm cube. So do you notice, right, okay, because of this contaminant, you end up using more Ag plus. You actually end up using a total of 24.6. You use more than what was expected. And because of that, right, okay, your answer in part C will also be larger than expected, right? Okay, you refer to C part 1. Okay, let's go back to our working here. Okay, imagine this was 24.6 or some bigger number. This number will be larger, this one will be larger, this one will be larger, right? And then your concentration will also end up being larger. Okay, this 25 doesn't change, okay, it's the same thing. Okay, the sample is still 25 cm cube. Okay, when they use the word contaminated, okay, it's just a little bit such that it doesn't actually affect this water sample's volume. Okay. So to answer the question here, okay, I acknowledge the complex also lah. Okay, that's what you can do if you want to. Okay, if there's ammonia, then it could have formed a complex. That's why you need more NH, you need more Ag plus to reach equivalence point. Okay, Ag plus to reach equivalence is larger than expected. That's why the answer is also larger than expected. Okay, these kind of questions you must always use the words larger than expected, smaller than expected. Okay, because it's not actually the correct answer, right? Okay, got a question in the chat. Can we say that the ammonia will produce OH minus that the Ag plus will react with? It is not wrong, but okay, I would say it's fine because NH3 does produce OH minus. You're not wrong. Okay, so but it's just not the main thing that they want you to think about here. Okay, next time when you guys see NH3 and there's silver in the question, right, you should think of this complex first. You shouldn't be thinking of the OH minus ions that Ag will react with. You're not wrong, okay, but I would say this is the most significant reason. Okay. All right, and with that said, okay, if there are no questions here, again, as I mentioned, this question here is very well set, I feel. Okay, it's quite a good question. Go and maybe perhaps redo it if you had trouble with this. Okay, and we're gonna take a break first, okay, before we move on to the final question of today. Okay, so I want you guys, we take a break until like, let's say 6:12 lah. Okay, we take an 8-minute break. Okay, just type in the chat also. Okay, break until 6:12. Okay, later on we come back with a final question. Okay, so break time. Okay, you got any questions? Okay, you can just ask me now also. Okay, I want you guys to try the last 2022 question that we haven't done yet. Where is it? Okay, it's question 4. Right, okay, so I want you guys to try question 4, but just do part A first. Okay, so 4A, this synthesis pathway. Okay, I'll give you guys about 8 minutes also, okay, to try to solve this synthesis question. All right, okay, time's up. Okay, let's go over the synthesis. Okay, this synthesis not as easy as the one that we saw just now. Okay, but you still just have to apply whatever you have learned. Right, okay. We have talked about synthesis techniques, okay, which makes your life a lot easier. Okay, so we're just gonna do that here. Okay, so first of all, right, we have ethene. Okay, ethene is made out of 2 carbons, and I did say just count the number of carbon atoms. Tartaric acid has a total of 4 carbons. Okay, so step-up reactions. Okay, we did mention before how step-up reactions are actually a lot simpler than it looks. Okay, because whenever there's any step-up reaction, okay, it only can involve a nitrile functional group, right? Okay, but the issue is, where does the nitrile functional group come in? Okay, before we look at that, we shall just identify the 2 possible nitrile reactions. One is nucleosub and one is nucleoadd. Okay, but when do you use which? Okay, I did tell you guys this before. You use nucleosub if there is no change in functional groups. Okay, if the number of functional groups doesn't change, then you just use your nucleophilic sub version to place your nitrile into the molecule. Okay, over here for nucleophilic addition, if the number of functional groups actually increases by 1, okay, or number of functional groups increases, then you will use the nucleophilic addition version to put your nitrile into the molecule. Okay, so we have these 2 options to try, and right off the bat, right, okay, we can decide for ourselves already. Ethene is only 1 functional group, but this guy has 2 functional groups. So since there's an increase in functional groups, we have to use the nucleophilic addition version. Okay, so that is what we're supposed to expect. And remember that nucleophilic addition of nitriles require a carbonyl compound. So somehow, right, okay, you need to find a you need to make a carbonyl compound somewhere in this mechanism. Okay, but where does that happen? Okay, because if you realize, they did give us a clue about structure B, right? C2H2O2. Now, there's absolutely no need to go on a wild goose chase and just try and error and see what this structure is. Definitely not. You shouldn't just be guessing wildly. Okay, you should be using this. Okay, so we know we want to form a carbonyl compound. And as you can see here, between these 2 steps, right, there is no step-up reaction happening because they did tell us that B still has 2 carbons. So the step-up reaction must happen afterwards, maybe here or maybe over here. Okay, so that's where we can, that's what we can infer. Okay, this first part here, we can just settle first. Okay, how are we supposed to go from ethene to the first stage and then to the second stage? Okay, the second stage, again, we are supposed to get something here called C2H2O2. Okay, so perhaps, right, okay, this is where we are slowly working towards, okay, the carbonyl compound. Okay, we want to get the carbonyl compound first before we can do anything else, right? Okay, so let's try that. So perhaps, okay, how do we turn it into a carbonyl compound? Okay, you don't have to care about A or B yet. Okay, just ask yourself, how do you turn an alkene into a carbonyl? Okay, so maybe first of all, you can start off with, okay, of course, you have to oxidize the compound, right? Okay, in order to form a aldehyde or a ketone, okay, you must have some sort of alcohol. And how do I turn this into an alcohol? Right, okay, there are a couple of ways. Okay, like perhaps, okay, we can just experiment first. If you just undergo addition to form an alcohol like this, you're probably just gonna get a singular aldehyde, right? Which doesn't fit the structure of B at all. Okay, we need to have 2 oxygens, as you can see from the molecular formula. Okay, so this doesn't really work. Okay, is there another type of oxidation that we can go with? Okay, alkenes, okay, we can undergo mild oxidation, right? Okay, remember that mild oxidation allows you to add both OHs to the alkene. Okay, then once that is done, right, okay, if you realize we have 2 primary alcohols, and that's when we can turn it into a double aldehyde. And that is the structure of compound B. It fits the molecular formula. Okay, and once we have done this really, right, then we still have this in mind, right? Okay, we still need to undergo a nucleophilic addition of our carbonyl. Okay, this is the carbonyl, and we can undergo nucleophilic addition, right? Okay, over here, we can turn it into OH and CN. OH, CN. Okay, so that is 3rd step, right? Is the nucleophilic addition. And finally, how do you get the 4th step? Okay, we're trying to turn this into a carboxylic acid, right? Okay, which is your tartaric acid. As you can see here, we can just turn the nitrile into your carboxylic acid in the 4th step. Okay, so let's look at the reagents and conditions. Okay, first one, mild oxidation. Remember, you can use H2SO4, you can use NaOH, okay, but you must use coal. Okay, must be coal. The second one, you must use dichromate, cannot use KMnO4, okay, H2SO4, and you must heat with distillation. Okay, don't forget all these control factors. Right, okay, and then finally we got step 3. Okay, for step 3, oh wait, not finally, but we can undergo nucleophilic addition, HCN trace KCN, and coal. And then for the final step, okay, it's just your acidic hydrolysis, H2SO4 heat. So they gave 7 marks for this. It is entirely possible that you will see a 7-mark synthesis in your exam. And when it does come out, right, and when you figure out the techniques and all that, right, it's actually quite an easy way to get 7 marks. Okay, compared to, let's say, elucidation, that one requires a lot more effort, right? Okay, so with that said, okay, that's pretty much it for today already. Okay, of course, the next 2 parts of this question is quite short. Okay, you can go and try yourself, okay, on your own time. Next, I'll see some of you guys on Sunday, right? This Sunday, whoever that attends the Sunday class, yeah, okay, we will definitely go back to in-person teaching already. Today, I think today I already tested negative, but just had to make sure, just had to stay safe. So yeah, on Sunday, whoever's attending the Sunday classes, okay, we'll be back in person. Then the rest, okay, I'll see you guys next week in person also lah. Right? Okay, so yeah, if you have any more questions, you can just stay back and ask. Okay, I hope your practical also went well yesterday lah. Right? Okay, then